Okay, interpreting slope. We did do this, all right? So we'll probably go into this next, but all you got to do is take your slope, put it over 1. And so you have your change in y per unit change in x. So for every 1 kilogram increase of body mass, there is a 26.879 increase in metabolic rate, calories burned in 24 hours on average. Remember, you got to add in the on average, because in other parts of your scatter plot, this rate could be higher, and some parts it could be lower. This is just going to be an overall average from beginning to end in your scatter plot. And you can interpret the y-intercept too, but usually that's going to be kind of nonsensical. When lean body mass is 0, can you imagine a person that doesn't weigh anything? The model predicts a value of 113.2 metabolic rate calories. If you even threw in on average by mistake, that would be fine. But yeah, you can see you can't really have a person with a 0 body mass. So this is kind of a silly number, and that's the way it is mostly for y-intercepts. All right, so you probably already did this homework, so we'll forego it and close out of here. And as a continuation, this will be your homework, and we'll just do the first one together. So strap in as I read this. The paper, Arthroscopic Distal Clavicle Resection for Isolated Atraumatic Osteolysis in Weightlifters, and they reference a source, gave the following regression on x equals age and y equals days after arthroscopic shoulder surgery, I guess, before being able to return to the sport. All right, so here's your slope right here for interpreting it. And you just go ahead and write that over 1.272 over 1, and that would be days over years of age, okay? So for each increase of 1 year of age of the patient, there is a 1.272 extra days to heal from surgery on average. All right, so when you have to interpret the y-intercept, that's going to get silly, because here's your y-intercept. First of all, it's negative. So when a person is 0 years old, when you plug in a 0, that should just give you your y-intercept, right? They take negative 5.5 days to return to weightlifting. Okay, ridiculous. But every so often you do get a y-intercept where it's not ridiculous. And it will actually match up and make perfect sense. But in so many of these, the y-intercept is just silly. If you're asked to interpret it, do it, but be prepared for it to kind of sound a bit funny. All right, but slope is a much more meaningful thing. So we did the first one, and you can do the rest. When you look at this one, or not this one, but this one, see the negative slope? That's going to be for each increase in 1 minute a patient waits to receive defibrillation, there is a 9.3% decrease, right? The negative slope, that's a decrease per increase in unit X in survival rate on average. So be prepared for that. And you can do this. The key's posted so you can get some guidance for it. Okay, so there is that. So that brings us to the new thing, which is not very long, and this is coefficient of determination. All right, that's the r squared. The problem is with r squared is that people tend to mistake it for r. All right, best I can tell you is that r came first, so it's coefficient of correlation, which is a letter before coefficient of determination, which is r squared. You learn that second. So C comes first and then D. R comes first and then r squared. Just don't mix them up. All right, we don't need this. I thought I'd removed it. Okay, coefficient of determination, r squared. Hey, this is the nice thing about it. Remember that R was not capable of providing any kind of proportional reasoning. Like an R of 0.8 is actually way more than twice a linear strength than an R of 0.4. Well, here R squared does give the fraction or proportion of the variation in the value of y that is explained by the variation in x, or it gives the proportion of the behavior in y that can be explained by the behavior in x, right? Some people prefer the variation explanation. Some people prefer the behavior. It's going to work either way. I actually like to think in terms of behavior, but whatever. All right, so here an r squared of 0.84 does have twice the linear strength of an r squared of 0.42. So we can make that comparison. Okay, so r squared is a comparative measure, r correlation isn't. Yes, you can look at them and say, okay, this has a better linear fit than this one does, but you can't do any proportional reasoning. Couple of things. First of all, r squared will always be positive, and that's going to be important because if you have to go from r squared back to r and your relationship is negative, you won't see that when you take the square root. You're just going to have to go, oh, my slope is negative, my r is negative, okay? So you can backtrack or backstep from r squared to r, but keep in mind there may be a sign issue when you do it. The other thing I want to bring up while I'm thinking about it is that just because r or r squared is high, you know, close to 1, that does not make it a linear relationship, okay? It's the linear relationship that determines whether or not you use r or r squared, right? But not the other way around. So if I just say, you know, I've got these two variables where r is 0.9877, don't tell me that that is necessarily linear without looking at the scatter plot. Trust me, you can have a curved relationship that you'll just slip into a calculation for r as a linear summary, and you can get high correlations. It does not mean that if r is high that your original data set was linear. Just that's a mistake people make. All right, r squared is a measure of how successful the regression is in explaining the response. It's a measure of how well your LSRL predicts the response for any given x, okay, given that we're in a linear model. So r squared means that 84% of the variation in y is accounted for or explained by, or 84% of the behavior in y explains is explained by the behavior in x, or 84% of the variation in y is accounted for by the linear model on x. There's a lot of ways to say it, but pick one and treat it as though it's a script, all right? Because that's how you interpret your coefficient of determination. For me, I would probably say an r squared of 0.84 means 84% of the behavior in y is explained by the behavior in x. That's how I would do it. Make sure to use the context. None of these things is in context because it's just an example, but in the real world there is context. So for the problem that we just did, if you go back and look at your summary numbers on page 8, you'll see an r squared of 0.7477. All right? If you're asked to interpret that, you would say 74.77% of the variation of the metabolic rate can be explained by the variation in body mass, or 74.77% of the variation of the behavior of the metabolic rate, remember that's your y, can be explained by the variation or by the behavior in body mass. All right? Yeah, you're always explaining y in terms of x, because x is always increasing, right? Y either increases with it or decreases with it or acts sort of haphazardly. All right, the more haphazard that it behaves as x increases, the more you can account for what y is doing by something other than x. So in this case, 74.77% of the behavior of the metabolic rate can be explained by the behavior in body mass, and about 25 or 24% is explained by something else, which we don't happen to know, but that's how you kind of look at those things. Okay, another way to say it. All right, so there is the assignment, and I'm trying to think if there's anything else. I showed you how to make predictions. I showed you computer output. We talked about R squared. We talked about slope and Y-intercept. That's actually quite a bit. So you may need to study up on this stuff and make sure you get R and R squared, separate in your mind. R is correlation. R squared is coefficient of determination. Correlation does not give you proportional reasoning. Determination does. All that kind of thing. You just have to be quick off the bat on those concepts. So I believe that's everything. And I'm just going to call up my little program here, cut it short, and I will bid you a fond farewell.